Hello everyone, welcome to a new episode of Learning from Home. Today we are going to learn about physical quantities and their units. We will find out what physical quantities mean, the prefixes that go with them. We will learn in detail various length measurements, including a brand new instrument called the vernier caliper. We will also learn about area measurements, volume measurements, mass measurements, and many other measurements. Physical quantities are actually quantities that can be measured by an instrument. They have a numerical magnitude, meaning they have a numerical number followed by a unit. For example, mass is a physical quantity. In this case, the mass of the stone is 500 grams. So the physical quantity known as mass, in this case, has a value or a numerical magnitude of 500 and a unit of grams. Now all physical quantities have the SI unit, which is the international unit. The international units ensure that all parts of the world measure the same quantity to the same value. For mass, the SI unit is the kilogram, symbol kg. For temperature, the SI unit is the Kelvin, symbol is K, not degrees Celsius or degrees centigrade. The SI unit of length measurement is the meter. It's not the kilometer, it's not the centimeter. The SI unit of current is the ampere, named after the French scientist Ampere, symbol is capital A. The SI unit of time is second, symbol S. It is not minutes, it's not hours. The prefix is a number that you attach to a physical quantity as a short form denotion of a number. As an example, mega refers to a million, so it has 6 zeros. When it has 6 zeros, it's 10 to the power of 6. So for example, if we have 5 mega meters, that is equivalent to 5 million meters. Kilo means 1,000 with 3 zeros, so it's 10 to the power of 3. So 6 kiloseconds refers to 6,000 seconds. Deci is divided by 10, so it's 10 to the power minus 1. Centi is divided by 100, so it's 10 to the power minus 2. Milli is divided by 1,000, so it's 10 to the power minus 3. Micro is divided by 1,000,000, so it's 10 to the power minus 6. Nano is divided by 1,000,000,000, which is 10 to the power minus 9. Now the base unit is a unit that doesn't have any prefixes. As an example, 23.4 kilometers. The meter is the base unit, the K is the prefix. Another example, we have 5.3 centimeters. So 5.3 is the magnitude. Centi is the prefix, which we replace by 10 to the power minus 2. And meter is the base unit, we leave it as it is. As an example here, a textbook is 2.6 centimeters thick and it contains 500 sheets of paper. What is the thickness of one sheet of paper? Obviously, we will have to divide 2.6 centimeters by 500 sheets to get the thickness of one sheet of paper. And when we do that, we get the answer 0.0052 centimeters. Now 0.0052 centimeters is 0.0052 times 10 to the power minus 2 meters, because the centi is 10 to the power minus 2. And we can also convert 0.0052 into 5.2 multiplied by 10 to the power of minus 3. And in doing so, we shift the decimal place 3 places to the right and we get 5.2. Alright, so therefore 0.0052 multiplied by 10 to the power minus 2 is actually 5.2 multiplied by 10 to the power minus 3 and multiplied by 10 to the power minus 2, in which case you get 5.2 multiplied by 10 to the power minus 5. Of course, you keep the base unit. Another example, we need to identify the measurements from the smallest to the largest. The best thing to do is to convert everything to meters. Let me just make this a little bit bigger for you to see. Alright, so in the case of the centimeters, we change centi into 10 to the power minus 2. 10 to the power minus 2, another 10 to the power minus 2, we get 10 to the power of minus 4. So this becomes 6.18 multiplied by 10 to the power minus 4 meters. Kilometers, we change the kilo to 1,000, 10 to the power 3. So this becomes 6.18 multiplied by 10 to the power 2 and multiplied by 10 to the power 3 meters, in which case we'll get 6.18 multiplied by 10 to the power 5 meters. Let me just make this clearer a little bit. Okay, what about the nanometer? Well, the nanometer is 10 to the power minus 9 meters. Nano. Nano is also nino. So nano becomes 10 to the power minus 9 meters. Alright. Then 6 minus 9 is equals to minus 3. So we end up with minus 3 meters. Finally, micro. Micro is 10 to the power minus 6. So we convert the micro into 10 to the power minus 6. 8 minus 6 is 2. So we end up with 10 to the power 2 meters. That's it. Hi, let us now learn about length measurements. So we're talking about measuring distances. The SI unit of distance is meters. The instruments we need to learn to measure things with are the measuring tape, the meter rule, external and internal calipers, and the vernier calipers. The measuring tape can be several meters long. As such, it can be used to measure the dimension of the floor or the room. Its precision is 0.1 centimeters. So it is precise up to 0.1 centimeters. So it has the same precision as your normal ruler, in other words, just that it is soft and it can be used to measure items that are not straight, items that are circular, items that are bent. So they are typically used to measure circumferences. The meter ruler is a meter long and it is used to measure straight objects to a precision of 0.1 centimeters. There are some precautions when using a meter ruler. First, you have to ensure that no gap exists between the object and the ruler. Secondly, you have to ensure there is no parallax error. To eliminate parallax error, one must always take the measurement directly above it. If we were to measure from here, our reading will be too short. If we measure from here, then the reading will be too long. We must also avoid end error. So if the ruler is chipped, then the end may not necessarily start from 0. That will be an end error. Or if we forgot to place the object at 0 centimeters, then we are also committing an end error. Let's try out an example. What is the accuracy of this instrument? Should I say precision of this instrument? It will be 0.1 centimeters because that is the length of the smallest division. Where do we place the eye? For an accurate measurement, we place it directly above at B. And what is the length of the metal block? We need to calculate the length of the metal block by taking the final measurement and subtracting it from the initial measurement. So we will do this is 7.3 centimeters and this is 5.2 centimeters. So we subtract 5.2 from 7.3, we end up with 2.1 centimeters. That's it. Hi, let us learn about using the calipers. There are two types of calipers. The external calipers are used to measure the external diameter of an object. The internal calipers are used to measure the internal diameter of an object. The vernier caliper is 10 times as precise as the normal ruler. So its precision is 0.01 centimeters. It comprises of a main ruler or the normal ruler with a normal precision of 0.1 centimeters and a vernier ruler with a precision of 0.01 centimeters. How do we use the vernier calipers? Initially, the vernier caliper would be closed, and when it is closed, the main zero would be aligned with the vernier zero. So this line here is the main zero. So when the jaws are closed, this vernier zero here will be aligned with the main zero. To take a measurement, we will have to open up the vernier caliper, the jaws, and when the jaws stop moving, that is the measurement. In other words, the measurement is between the main zero and the vernier zero. So the vernier zero tells you where the reading is. This is very important. The vernier zero tells you where the reading is. Now in this case, let us see where the vernier 0 is. The vernier 0 is lying somewhere here, which is right after 12.5. Sorry, my bad, 2.5. So this number here is 2.5 centimeters, right? So the main ruler, which is the normal ruler, can give you a reading of 2.5 centimeters, but you know the actual reading is somewhere between 2.5 and 2.6 centimeters. So 2.5 is given by the main ruler. So the second decimal place is given by the vernier ruler. Now, what is the second decimal number? To do that, you need to find out the marking that is aligned both top and bottom, and this line is the line that's aligned top and bottom. Now, because the second decimal place comes from the vernier ruler, so we obviously have to read the number from the vernier scale. And if we count the numbers, 1, 2, 3, 4, 5, this is number 5. It's number 5. So the second number for this measurement is also 5. So this measurement is 2.55 centimeters. The vernier caliper has 3 parts. The tail is used to measure how deep an object is. The internal jaws are used to measure the internal diameter of an object, and the external jaws measure the external diameter of objects. This is another example of a vernier caliper reading. Now first, we read the main scale. The main scale reading is given by the vernier 0. Now the vernier 0 lies somewhere between this marking and this marking. So it lies between 2.1 and 2.2 centimeters. So it must be 2.1 something centimeters, a little bit more than 2.1 centimeters. If we had only a normal ruler, then we had to estimate between 2.1 and 2.2 centimeters. We can't say for sure if it's 2.14 or 2.15 or 2.16 centimeters. We can only say it's either 2.1 centimeters or 2.2 centimeters. But now with the vernier caliper, we can find out the second decimal place. First, we need to find out which marking is aligned. Now this marking is aligned. Now remember, the second decimal place is given by the vernier ruler, and from the vernier ruler we see this is number 5, and hence the second decimal place is 5. So 2.1 centimeters plus 0.05 centimeters, we get 2.15 centimeters. Let's now look at zero errors. A zero error is one that occurs when the zero marking of the main scale isn't aligned with the zero marking of the vernier scale when the jaws are fully closed. There are 2 types of zero errors, the positive zero error and the negative zero error. In the case of the positive zero error, when the jaws are closed, there is actually a positive reading. When the jaws are closed, the two zeros are supposed to be aligned with each other. But in a positive zero error, when the jaws are supposedly closed, there is still some positive reading, and that is why this is called a positive zero error. In the case of the negative zero error, when the jaws are closed, there is a negative reading on the vernier scale. So much so that you need to slide the vernier scale slightly to the right before it reaches 0. So the vernier scale is actually short of reading. So the negative zero error means that right at the start, the vernier caliper is short of reading. How do we handle zero errors? For a positive zero error, because there is something extra right from the start which isn't supposed to be there, you need to minus off the error from the measurement. For the negative zero error, right from the start, you are short of reading. You are lacking in some reading. So hence, you would have to add back the error. You have to add back the error to the measurement. Let us try some examples on the reading of vernier calipers. Example A, the vernier 0 is situated here, right between this marking here, which is 6.1 centimeters, and this marking here, which is 6.2 centimeters. In other words, the reading falls somewhere between 6.1 and 6.2 centimeters. So it must be 6.1 something centimeters. 6.1 something centimeters. The second decimal place comes from the vernier ruler. And the vernier ruler, this marking is aligned, and this marking is marking number 5. Hence, the second number is the number 5. So the reading is 6.15 centimeters. For example B, the vernier 0 lies here, somewhere between this marking, which is 3.6 centimeters, and this marking, which is 3.7 centimeters. So the reading is 3.6 something centimeters. So the main ruler tells you is 3.6 something centimeters. The second decimal place is given by the vernier ruler. Now if you look at the vernier ruler, we find this marking is aligned. And for the vernier ruler, this is marking number 6. Hence, the reading is 3.66 centimeters. In example C, the vernier 0 is here. So the reading is here, somewhere between 8.1 centimeters and 8.2 centimeters. So the reading must be 8.1 something centimeters. So the 8.1 comes from the main ruler, the normal ruler. The second decimal place comes from the vernier ruler. If you look at the vernier ruler, we see these marking aligned, and this is marking number 8. Hence, the answer is 8.81. Let's take a look at another example. In this case, we have a zero error, and it is a positive zero error because the vernier 0 lies to the right side of the main 0. So there is already some reading right from the start. Now, what is the zero error? We need to find the marking that's aligned with each other, and that marking is this, which is marking number 4. Hence, the zero error is positive 0.04 centimeters. Now, what is the reading in diagram B? Well, the reading lies somewhere between 5.2 centimeters and 5.3 centimeters. So the reading must be 5.2 something centimeters. What is that second decimal place? We look at the marking that's aligned, which is marking number 9. Hence the reading is 5.29 centimeters. Now a positive zero error is compensated for by minusing it off from the reading. So 5.29 centimeters minus 0.04 centimeters, we end up with 5.25 centimeters. So the true value, the true measurement of the wooden block is 5.25 centimeters. Let us now look at another example with negative zero error. In this case, the vernier 0 is behind the main 0, so it is short of reading right from the start. For negative zero error, you have to read from the right hand side. First, let's find the marking that's aligned. So this marking is aligned. Now when we read from the right hand side, we find that marking number 1, 2, 3, 4 is aligned. So the zero error is negative 0.04 centimeters. What about the reading in diagram B? The reading in diagram B falls between 1.7 centimeters and 1.8 centimeters. So the reading is 1.7 something centimeters. Now which marking is aligned? This marking is aligned, marking number 8. So the reading is 1.78 centimeters. Hence, the true value, the corrected value, would be 1.78 plus 0.04 centimeters, because a negative zero error means you're short by 0.05 from the start, so you have to add back the 0.04 and you will get 1.82 centimeters as the true reading. Let us now look at area measurements. The standard SI unit for area is the square meters. Other units of area are square millimeters, square centimeters, and square kilometers. The formula for the area of a square is length multiplied by length. The formula for the area of a rectangle is length multiplied by width. The formula for the area of a triangle is half multiplied by length multiplied by height. The area of a trapezium is half the sum of the parallel sides multiplied by the width. Now if you look at the trapezium, if we take A multiplied by H, that will be too short or not enough. If we take B multiplied by H, then that will be too much. So one is too much and one is too little. So the correct length is somewhere between A and B. In fact, exactly between A and B. If we can find the length that is exactly between A and B and we multiply that by H, we would get the correct area. So where is the point or the length that is that directly between A and B? Let's mark it out here. Okay, exactly in between this point and this point. If we do that, we will be able to cut this piece of triangle and put it in to here, thus completing the left side of the rectangle. We can do the same on the other side. We took the middle part, the middle point, midway between this point and this point, and then we cut this piece of triangle and we place it here. When we do that, we complete a rectangle with this length and this height. The height is still h, but what is the new length? The new length is exactly between A and B. What is exactly between A and B? Exactly between A and B is A plus B divided by 2. Hence, the formula for the area of a trapezium is A plus B divided by 2 multiplied by h. Let's move on to area of a trapezium. Area of a trapezium is length multiplied by h. We can do the same experiment. We can cut this piece and put it here. We end up with a rectangle of length L and height h. The area of a circle is pi r squared. To find the area of irregular objects, we need to use approximation. We put the grid over the shape and we count the number of squares. If the square covers more than half of the square, then it is counted. If the square covers less than half of the shape, then the shape is excluded. So the area of an irregular object is the total number of squares multiplied by the area of one square. In this case, the area of one square is 1 square centimeters. Let us now look at volume measurement. The SI unit for volume is the cubic meter. Other units include millimeter cube, centimeter cube, milliliter, and the liter. There are various instruments for measuring volume. We have the beaker, which makes rough volume measurements, the measuring cylinder that measures volume up to 1 centimeter cube precision, the pipette that measures volume up to 0.1 centimeter cube precision, and the burette that often measures up to a precision of 0.01 centimeter cube. Thus, it is the burette and the pipette that can perform accurate, precise measurements. When making volume measurements, it is important to take into account of the meniscus. The meniscus is the curvature of the liquid due to the measuring instrument. In this case, the true value is obtained from the middle part that is not touching the glass or the container, because it is the adhesion of the liquid to the glass that causes the liquid to curve upwards and distorts the reading. So since this is a distorted reading that is affected by the glass, it is to be discounted. The true reading is given by the middle part that is unaffected or untouched by the glass. Water normally exhibits meniscus that curves upwards, but if you have mercury, then the meniscus curves downwards. In this case, we apply the same principle. The true reading is given by the middle part unaffected by the surrounding glass. So that is the true reading. The glass part causes the liquid to bend and thus gives the wrong reading. To measure the volume of irregular or regular objects, we can use formulas. For a cube, the formula for the volume is length times width times height. In the case of a cube, it's actually length times length times length because the lengths are all the same. In the case of the cuboid, the length and the width and the heights are not the same, and hence the volume is length times width times height. The volume of a cylinder is the base area multiplied by the height, which in this case is L, and the base area is pi r squared. Hence the volume is pi r squared multiplied by the length. The volume of a sphere is 4/3 pi r cubed, r being the radius of the sphere. To find the volume of irregular objects, we have two methods. 1. The measuring cylinder. 2. The displacement can. To use a measuring cylinder to measure volume of irregular objects, we first fill the measuring cylinder to an initial volume. Then we place the irregular object into the cylinder and the level rises to a final volume. We take the final volume minus the initial volume and we will obtain the volume of the irregular object. In the case of a heavy, or should I say lightweight object, which doesn't sink like a cork, we can tie a stone to the cork to sink the cork into the liquid. We can then deduct the volume of the stone from the volume measurement. Finally, we can also use the displacement can to measure volumes. First, we fill the displacement can to the brim. Next, we plonk the object into the displacement can. The water gets displaced and enters the measuring cylinder. The volume of water captured by the measuring cylinder is the volume of the object. Let us now look at mass measurements. Now, mass is the amount of substance in the body. It will never change even if you go to the moon or to outer space. The SI unit for mass is the kilogram. Other units of mass measurements are the milligram, the gram, and the ton, which is 1,000 kilograms. Instruments to measure masses are the beam balance and the electronic balance. So this is an example of the electronic balance. What is a beam balance? A beam balance is basically a scale. A scale will balance when you put equal masses on each side. So if a 100-gram mass balances a scale that contains a piece of fish, then that fish is also 100 grams. Even if you were to take the scale to the moon, where the gravitational pull is weaker, the beam balance will still balance. The 100 gram will still balance another 100 gram. Temperature measurement. Temperature is a degree of hotness or coldness, and the SI unit is Kelvin. Other units are the degree Celsius or the degree Fahrenheit used by the Americans. Instruments include the thermocouple, the liquid in glass thermometer, which is hardly ever used anymore, and finally the time measurement. SI unit is seconds. Other units include the minutes, the hour, the days, and the years. Instruments include the stopwatch, the digital watch, and the alarm clock.